This video is going to present some ideas on limits. So limits, in a nutshell, are basically going to be the numerical behavior of a function's output, like what the graph does with respect to y values, with respect to given input values. So, as x gets really big, as x gets really small, as x goes to a number, what does the graph do? What does the function behavior do? And that's different for different functions. And a lot of times you can look at the graph, and sometimes you can look at numerically what the function will do when you put the input values in that you're interested in. So the first two examples I have here are polynomials. And polynomials, are the curves that have different shapes. And polynomial shapes are always based on what's called the leading term, or whichever term has the highest exponent. So in this first example, the 3x squared minus 5x plus 7, that's a parabola, power of 2. The graph ends up looking like, roughly that concave up parabola. But more importantly, if you look at the fact that you want to know what the function behavior does as x values go to infinity. So as x values get really large, when you go to plug them in, you can really focus on that highest power term, that leading term. And if you take a 3 times x squared and that x value just gets bigger and bigger and bigger, and the square of that number gets larger and larger and larger, and times it by 3, the function value for this polynomial is going to get extremely large. So we say the limit as x approaches infinity for this polynomial actually equals positive infinity. And you can see on the graph, as the x values get larger and larger, the graph just shoots off up being in the direction of y for infinity. Okay. Second example, another polynomial, but now our leading term with the highest coefficient. It's not the one in front, but it's the term with the highest exponent. It's called the leading term. This happens to be a cubic function, 7x squared minus 9x cubed, and we're interested in what the function behavior looks like as x gets extremely small. So if you want to look at a graph of it very quickly, it sort of does this number. Excuse me. And if we're trying to look as x values get extremely small, so we're going to look in this region of the graph. So, like x is -3, the next is -15, the next is -1,000, the next is -2,756,212. As x gets very large in the negative sense, what happens when you plug it into that function? Well, if you cube a negative, it's still negative. And if you do a -9 times a negative number, it's going to be positive. So no matter how negative x gets, when you multiply it by -9, you're going to end up with a positive answer. And the limit, or the function value, as x goes to negative infinity is going to be positive infinity again for this function. Again, it's just the function behavior in the particular x area that you're interested in. Okay, so there's a couple polynomial examples. The next two have to deal with these rational functions, the 1 over x squared. So we want to look at this example that says, find the limit as x approaches infinity of 1 over x. So that's going to take us to a number 1 divided by a number that's just going to keep getting larger and larger. And if you remember about fractions, think of it 1/2, 1/3, 1/4, 1/8, 1/9, 1/100th, 1/1000th. The larger the denominator gets, the smaller the fraction gets. So if that denominator gets larger and larger, 1 over that is going to keep getting smaller and smaller. And so the limit for this function is actually going to be 0, because as x gets very large, that 1 over x, the output, the function value, is going to get closer and closer to 0. Now you're welcome to graph this one if you like. It ends up being a curve in the first quadrant, and then this curve in the second quadrant. And if you looked at x as it got larger and larger, you'll see that the graph will slowly try to approach the x-axis, but it'll never quite get there because the function can never be 0. That's part of the range. But for this one, as x gets larger and larger, the function value tries to approach 0, but it will never quite get there. Okay? For the other function, the 1 over x squared, if we look at the limit as x goes to negative infinity, imagine plugging in negative numbers into the denominator. You're going to plug negative numbers into a denominator, and then you're going to square them. So the output will always be positive, and you'll have 1 over a positive number where the denominator, much like the last example, will get larger and larger, so the fraction itself will get smaller and smaller. So this is another example of the limit as x goes to negative infinity of 1 over x squared is also going to be 0. If you wanted to look at a sketch of a graph of this function, it's very similar to the last one, except they live in the first and second quadrants. And if you follow the graph as x goes to negative infinity, you'll also see that it tries really hard to touch that x-axis so that the function can get lower and lower and approach 0, but it'll never quite get there. But the limit for this function is as x gets extremely small, the function itself tries to get as close as it can to 0. So the limit value for this function is 0. Okay. Here's a couple more, still similar. You have the limit as x goes to infinity of x over negative 4. That x over negative 4 is the same as 1 over x to the 4th. It's almost identical to the last two that we've done. If you, again, focus on the x being extremely large, if you take extremely large values, plug it in for x, raise them to the 4th power, the denominator gets large, the fraction itself gets small, and so this limit is another answer of 0. Next example, pretty similar, but we can look at it. 2x to the negative 1 is the same as 2 over x. And this time we're looking for the x values to get negative in the sense here, but it's like 2 over negative 3 and 2 over negative 5 and 2 over negative 8 and 2 over negative 100. So that fraction still gets smaller and smaller and smaller in the negative sense. And as x goes to negative infinity, that fraction itself, you can graph this, but it's going to have a very similar shape to the 1 over x. The curves might just be slightly different. So as x goes to negative infinity, those fraction values still try to get closer and closer to 0. So the limit for that function is also 0. Okay. This third example on this page is only slightly different because it has the addition of the 2 at the end. So if I rewrite the limit as t approaches infinity and rewrite the t to the negative 3 as 1 over t cubed, the plus 2 is still part of the function. But more importantly, this 1 over t cubed portion of the function, because it is another one of those 1 over a number that's just going to keep getting bigger and bigger and bigger, that portion of the function will end up going to 0 as far as a limit value for that function. So if that 1 over t cubed quantity goes to 0, what you're left with is this value of 2. So as the t values get larger and larger, the output or the function values will get closer and closer to 2 for this example. Okay, here's another similar example. We've got 5 minus 7y to the negative 2. If I rewrite that, I get limit as y goes to negative infinity of 5 minus 7 over y to a positive 2. This time we're looking at y values as they get negatively large. But again, we're plugging a negatively large number into a denominator and squaring it. So the fact that it's negative is just going to make it positive when we square it. So this becomes 7 over a larger and larger number. So that part of this function will actually end up going to 0, like the value of the function when y gets extremely large in the negative sense. That portion of the function will go to 0, and what you're left with is the value of 5. So 5 is the limit value for this function when y goes to negative infinity. That's all that's left. The fractional portion ends up going to 0, so your answer here is 5. Okay. Sometimes you'll have one-sided limits, and one-sided limits just sort of look at what the function does as you approach a value from different directions. So you'll see this notation like x approaches 0 with a little plus sign in the superscript. That means that you're approaching 0 from the right. So like on this graph here, here's 0. As I approach 0 from the right means I actually come into 0 from the right side of the graph. If I approach 0 from the left, that's going to have a little superscript of a negative sign, and that means from the graph I'm coming in from the left and seeing what happens to the graph. So be careful with the directionality of this, but from the right approaches it from the right side of the graph, and from the left approaches it from the left side of the graph. So if we take the function 1 over x, for example, and we want to look at what the limit does as x goes to 0. Well, if you approach 0 on this graph, you can see that the graph goes in different directions. But if we break apart and look at the limit as x goes to 0 from the right of 1 over x, that's where we see, as x gets closer and closer to 0, the function values itself go up to positive infinity. However, if you look at x, the 1 over x function, as x goes to 0 from the left, you see that the graph ends up trying to get infinitely large in the negative sense because it shoots down the y-axis. So as x approaches 0 from the left, those function values approach negative infinity. And a lot of times, if you're asked just if the limit as x approaches 0, some people would say that it does not exist because it's not the same from the left and from the right. But if you break it apart into these right side and left sided limits, you can give the separate function values. But as it goes to 0 on a whole, it doesn't go to the same place. And when we talk about this more later, that'll be a discussion. It just doesn't exist if it doesn't go to the same place. Here's another one for a limit as x goes to a number. As x goes to 0 for this function, you get really close to 0. X cannot be 0. Looking at the graph for 1 over x squared, there's a curve in the first quadrant, curve in the second quadrant. 0 is there. Here's their origin at 0. And as x goes to 0, whether it's from the right or from the left, so here's x going to 0 from the right, on the right-hand side, and here's x going to 0 from the left on the left-hand side. You can see both of those function values, regardless of what they are, they end up, the graph itself goes up to positive infinity on the y-axis. So the function values, the function behavior of 1 over x squared, when x gets really, really close to 0, the function values go to infinity. Because you're taking 1 and dividing it by a smaller and smaller number, and it has the opposite effect of the larger number. If you take 1 and divide it by a smaller and smaller number, that number is going to go into 1 more and more times. So the value of this is going to blow up and get huge. So that's why we say the limit as x goes to 0 of 1 over x squared ends up being infinity. So hopefully this gives you a little more insight on how to approach limit questions for the beginning of this chapter.